In the first lecture on classical mechanics, we'll discuss some of the mathematical preliminaries which will be required during the entire course. So when you talk about coordinate system in classical mechanics, and this classical mechanics that we are going to discuss here does not include special relativity, the coordinate systems only have the spatial parts. So once I have special relativity, I have to include the time also, but here time is more like a parameter in which everything happens. So this is only the spatial parts that we have to talk about with the coordinate system. And we can choose different types of coordinate systems. And what is the meaning of these different types of coordinate systems? Let us go by examples. So let us talk about Cartesian coordinate systems. What are the Cartesian coordinate system? Well, if I'm dealing with 3-dimension, the Cartesian coordinate systems are usually, that they're referred by x, y, and z in 3-dimension. It can be u, v, and w also, or anything, any three symbols that you want to choose. Usually it is referred as x, y, and z. And how does this x, y, and z changes? So I can draw a picture here where x changes if like this along a straight line, then y changes along a straight line which is perpendicular to that. So when I say Cartesian, this is rectangular Cartesian coordinate system. Rectangular means that the three axes are perpendicular to each other, and then z changes perpendicular to both x and y. So that's your idea of a Cartesian coordinate system. So three axes, three variables x, y, and z, they changes along straight lines which are perpendicular to each other. We can also have a cylindrical polar coordinate system. Here the symbols you write usually as rho, or I write usually as rho, theta, and phi. And it is a little different than the Cartesian. And often it is drawn in the backdrop of Cartesian just to have an idea about what's happening with respect to the Cartesian. So I'll do the same. So I'll just first put the backdrop of Cartesian. Backdrop means I'm just putting the Cartesian things over here, and then I will change the color, and with some other color which I don't know what it is, I'll try to draw another set of coordinate system. So what does a coordinate system do? It specifies the coordinate of a point and say this is the point we are talking about. And for this point, the Cartesian coordinate system, in the Cartesian coordinate system, why do I write z first? I have no idea. The point is denoted by three numbers, one for x, one for y, one for z. So let's call them x1, y1, and z1. And the same point in the cylindrical polar is represented by three different numbers, and it's cylindrical polar, so you should have rho, phi, and z. So rho 1, phi 1, and z1 gives you the same point. So how do I get this? Well, so let me just again put the point over my Cartesian system, and the way I get the three axes, three values x1, y1, z1 for the Cartesian system is this. So I draw a perpendicular to the xy plane. The length of that perpendicular is my z1, and then this distance is essentially y1, and this distance is essentially x1. Here, when I do cylindrical polar, my z remains the same, z1 remains the same. So I take a projection here, so this is z1. But then I don't have x and y here, I have rho and phi. So what I say is the distance of this point, so this point is in the xy plane, remind you. Then this distance I call rho, and this angle which it makes with the x-axis, I call it, so let me write rho over here, and this angle I call phi. Okay. Same point can be now denoted by rho1, phi1 and z1. And you know that I have the spherical polar system as well. And I can have many infinite number of other coordinate systems, but these are the three systems that coordinate systems that you always learn in your undergraduate studies. So I'll just stick to them to make the point that I am going to come to. And you can fill in the gap over here. You already know what are rho, theta, and phi. I'm not going to bother you telling it again. So these are the three coordinate systems, and it just tells you that the same point is denoted by xyz, rho phi z, or rho theta phi in the three different coordinate systems, and how are those numbers x1, y1, z1, or rho 1, theta 1, phi 1, or rho 1, phi 1, z1, or rho 1, theta 1, phi 1, which will come for the uh, spherical polar case, how are they measured? It doesn't tell you anything more than that. And coordinates itself, however, does not tell us anything about the geometry of the space we are interested in. For that, we need to devise other quantifiers which will depend on these coordinate systems. So first of all, let us ask the question, once I know this one point, I want to put in one point here, what if I put in another point? And I say I put in another point which is there. Okay. And between these 2 points, I ask the question, what is the distance between these 2 points? So distance between 2 points. So I want to know the distance between any 2 points, but you see, it is better to first write down the distance between 2 points which are very nearby. Because if I know that distance between 2 points which are very nearby, so if I know the infinitesimal distances between two infinitesimally separated points, of course I can integrate always to calculate the distance along a curve if you wish. So later, this is, say these are two infinitesimally separated points, but later if I wish to calculate what is the distance between 2 points A and B along this curve, I can do that if I know the infinitesimal separation. So how do I calculate the distance between two nearby points? Now when I ask this question, it is not directly answered given any type of, given only the coordinate systems. To know this answer, I need to add some other properties which I called the metric property. Metric means measure, and the only thing that you can measure with coordinate systems is the distance between 2 points. So obviously the property of the distance should be called the metric properties. And it's a metric property of what I am calling system. So it's a metric property of what we call the space, and we'll discuss what is a space later on today. Okay. So I need to know what is the metric property of the space. So let us start with some examples again, and the space we'll choose is what you already know, 3D Euclidean space. What is a 3D Euclidean space? Where, well, you have learned about it in detail in your school days. You learned a lot of geometry in school days, and all those geometries are valid only in this particular type of space called 3D Euclidean space. And one of those properties is how do you measure the distance between 2 points. And the distance between 2 points, two infinitesimally separated points, let me write the square of the distance as dr square. And now it can be written in terms of these different coordinate systems. And you know what it is quite well. So if I write in terms of the Cartesian system, This is dx square dy square plus dz square. Okay, don't confuse 3D Euclidean space with this Cartesian coordinate system. They are different things. This is just how the xyz's are measured. It has nothing to do with any property of the space, so to speak. This is just one way of representing one point in that space. And now we are talking about what is the distance between 2 points in space, which can be different if it is not a 3D Cartesian space. So that we'll see later. 3D Euclidean space. Sorry. The same distance I can write as d rho square plus rho square d phi square plus dz square. So that's the polar coordinate system. And the same distance, again, there's some problem with the, okay, I can write as d rho square plus rho square d theta square plus rho square sine square theta d phi square. And you know that these three. So what is the third one? Third one is the 3D polar spherical polar coordinate system. The distance written in spherical polar coordinate system. Well, for all these three cases, the space that I am considering is 3D Euclidean space. And I cannot tell you a lot more about the property of the space, but that's what I mean when I say 3D Euclidean space. That the distance, or these are often called the metric functions, are written this way. So in general, so let us write down in general how will it look like. So it will, you write it this way. So say I have three coordinates, and now instead of writing at x, y, z or whatever rho, phi, etc., let me write these three coordinates more simpler way. Let us choose the three coordinates as x1, x2 and x3. So this dr square then just be dx1 square dx2 square, and there will be a part coming from dx3 square. Okay. Now, if you look at these different examples, in the first case, the coefficient of dx1 square is 1, dy square is 1, and dz square is 1. Second case, the first one is still 1, but the second one has rho square. So the coefficients of the square of the differentials can be anything actually. And let us write them in a certain form. So let us call this G11. Let's call this G22. Let's call this G33. And you can imagine an arbitrary case, I can have this type of terms also. So that's so-called cross terms. I'm sorry, again, 6-3 plus G31. And the space is obviously commutative, so it doesn't matter whether I write dx1 first or dx2 first. So I will have another term which is dx2 dx1, so but that should be same as this. So I'll just put 2 over here. So this quantity is G11, or I can write them as GII. So I can go from 1 to 3. So this can be any one of these essentially. So G13, G12, G11, all of them. And these are functions. These are functions of all x1, x2, and x3. Like this one is a function of rho square, which is x1. This one is a function of x1 and x2 both. In general, they can be function of all three coordinates. So this is called the metric function. Or you see that there is not one function. In the case of 3D, there are 9 such functions. 6 of them are independent. Because there is a symmetry if you think of Gij in a matrix form. So this type of objects are called tensors, which you will learn or have already learned, and they're called the metric tensor. It essentially tells you how to calculate the distance between two infinitesimally separated points in a given space, Euclidean space in this case, with a given coordinate system. So I have to give you both the space and the coordinate system, and then you will be able to tell me what is the metric, or the metric will specify these quantities. Now, so this is a special type of space which we call the 3D Euclidean space. Let us look at a different space. So instead of 3D Euclidean space, we look at only on the surface of a sphere, only on the surface of a sphere. Okay, so let's ask the question again. What will be the metric which is the infinitesimal, which gives you the infinitesimally separated distance between any two points on the surface of a sphere? What will it be? So if I call it dr square, you know what will it be, right? The surface of the sphere is at a certain constant radius. So I can just use the spherical polar formula, but the only thing I have to remember is that the radius is constant. So let us work it out starting from the spherical polar formula. So we start with spherical polar. Dr square is d rho square. So rho is the radius. If you remember, I called it rho. Usually it's called r. Called it rho because I wanted to call this as r. So on the surface of a sphere, rho is constant, so it's r. So what is d rho? Obviously it's 0, right? If it's constant, you do the derivative, it's 0. So on the surface of a sphere, dr square, d rho square is 0. This is capital R square. So this is just r square d theta square plus sine square theta d phi square. So if I ask you what is the metric tensor, first of all, you realize that it requires only two coordinates, theta and phi. So my metric GII, now we'll have four components. I can write them. The metric I can write as a matrix. So I can have G theta theta here, G phi phi here, and you see that there is no theta phi component, so these are 0. And what is G theta theta? It's 1. What is G phi phi? So which is this sine square theta. So without loss of any generality, I have assumed r square equals to 1 here. Let us try to see what happens if I try to write down the same metric in terms of cylindrical polar coordinate system. You see, here what happened is I started with the three-dimensional system, the metric in the three-dimensional coordinate, and then I imposed a condition here. So it's an algebraic condition. It's an algebraic equation on one of the coordinates of the 3D. And once I use that, this directly you see that it just becomes function of two coordinates. And it has only these two metric elements. So let's see what happens if I try to do the same thing with cylindrical polar. So there it will not be so simple. So let's see what happens. So this is to start with, and then simply dz square. And we know that rho square plus z square is essentially r square. So which is, if you remember, the r here will be, let me use some other color, so will be just this. This is my r, so which means this r is nothing by rho square plus z1 rho 1 square plus z1 square. So that's what I used here. So instead of a nice linear condition, the same condition becomes a quadratic equation. And now what you have to do, you have to eliminate z from this. You have to eliminate z from this using this. Okay, I'll leave it to you to do it, but you will see that you will obviously get back dr squared in terms of only two coordinates, but it will be a lot more complex. Or let us do it. So that's all right. So we can do a little bit of math here. So z square will become r square minus rho square. And if I calculate dz, z dz, that is minus rho d rho. So z square dz square is rho square d rho square. So if I use this, then you see that dr square now becomes, so I get d rho square from here 1, this is contribution from that. Dz square now becomes rho square d rho square by z square, which is r square minus rho square. And you can simplify it, that's up to you. I'll leave it here. Rho square d phi square. Okay, I can show that these two are equivalent, but that's all right. But you see that here, okay, so this you see that it will just become r square by r square plus rho square. And obviously in this spherical, in this cylindrical polar system, the component, the metric component, so this is which component? This is now my g rho rho component, and rho square is my g phi phi component, and they're more complex than that. So there is a nice thing here that if you choose the coordinate system, choose the right coordinate system, this coordinate system has the symmetry of a sphere, and we are looking at this coordinate system as a symmetry of a sphere, and you are looking at on the surface of a sphere, so obviously the metric is more simpler in this coordinate system compared to the cylindrical polar coordinate system. Okay, so I urge you to try to do the same thing with Cartesian, and we'll see that the metric coefficients become more difficult. If I have a 3D Euclidean surface space here, so if I ask the question, what is a 2D Euclidean metric, and that you know very well, is the Pythagoras theorem, tells you what is the distance between 2 points in terms of x and y. Right? If I do the same thing now, here you will see that so the dr square, this is I leave you as an exercise to work it out, but if I try to write down the metric in the surface of a sphere in 2D Euclidean coordinate system, what I have to do is I have to ensure that x square plus y square plus z square is equals to r square, and then eliminate this dz square just like we did here, and we will see that the metric will become a lot more complicated. Okay, so that is where you realize that this is not the 2D Euclidean space, this is a different space. This has this property of this is the surface of a sphere. Okay, so we understood that there are different types of spaces. Now if I consider a particular space, I can look at the same space from many different coordinate systems. the same space can be seen different coordinate system. Okay, so which means that I need to change the coordinate systems. I need to know how to change between the coordinate systems, and that need to satisfy certain properties. So when I talk about a space, it not only have this metric properties, it has another type of properties which is called the topological properties. And again, we are not going into the mathematical details of this, which we will not probably need in this course. So what we will do is we will rather try to understand things by examples. Okay, so let us take two sets of examples. One is this. So let us try to draw a 2D Cartesian coordinate, and these are supposed to be parallel lines. So this is just a 2D Cartesian coordinate system. I am drawing equal x and equal y lines. Right now I am drawing equal y lines, and I was drawing equal x lines. Okay. And let us choose a point, and let us identify that the points, these are the points which are in the neighborhood of these points. Neighborhood means it's near to these points. So if I consider this line and this line are near to these lines. Okay. Now I go to a different coordinate systems. So before I go to the different coordinate system, let me remind you, these are the lines where y equals to constant, and these are the lines where x equals to constant. Okay. And this coordinate system is x and y coordinate system. I go to a different coordinate system, which let's call that uv. So this is xy. I call it uv. Okay. And how does it look? So it looks, what do I plot first? So what do I draw first? So I draw the same lines. So this is y equals to c1, this is y equals to c2, and so on. This is x equals to c 100, x equals to c 50, so on. So c100, c50, all c's are some constant. So I draw the same lines in this, and say this looks like this. This line is nice, but then you get to see this. This is the same lines. Probably I will be able to draw less number here, but you get the idea. They bulge out. Similarly in the y. This is essentially something that you see in optics. It's called a Pincushion distortion. But anyway, so this is an example that I'm talking about. And let us draw the same points. So this is the point which corresponds to that dot, and the points which were near to it are these points. Sorry, not that. And the lines are this line and this line, right? So what has happened? Let us see. So this transformation has preserved certain things. So first of all, one point here mapped to one point there, right? If I ask all the points in the neighborhood of these points, they still stay at the neighborhood of the points. So neighborhood points here stays as neighborhood points there. What else? Curves. Curves which are in neighborhood here stays as neighborhood curves there. So these three curves are in the neighborhood, here also these three curves are in the neighborhood. Okay, so first thing is that the curves remains curves here. So a curve does not shrink to a point. Any curve doesn't shrink to a point here. And the second thing is that the neighborhood curves remains as neighborhood curves. Okay, so neighborhood curves here becomes neighborhood curves there. And it also has the nice property that if this is continuous and differentiable, this is also continuous and differentiable. So these two are said to have the same topology. The coordinate transformation that we have seen here can be think of in the following way, that the first one is a picture, and then if you use a lens which has some type of distortion, you will get the second picture after the coordinate transformation. So that's continuous transformation. Let us now have a look at a little different type of transformation. Let me first draw the horizontal and vertical lines corresponding to the equal x and equal y in our initial system. So these are the horizontal lines which corresponds to equal x, equal y, and these are the vertical lines which corresponds to equal x, just as we have done before. Now let us identify our point, which is around which we will see what happens in the neighborhood. So this is the point. We can then also draw the lines which are near to this point on the either side. So these are these two lines and the neighboring points. So let us all draw all 8 neighboring points, just like using stars. So these are our point over on neighborhood of which we get these 8 points and 2 lines. Now what we do is that we use a scissor and we cut this paper along this. And once I have cut this, I also open up the paper such that now the paper will look a little different. So let me try to draw and show you how it will look. So as you can see, the top part I have opened up. So this side has gone there, that side has gone there, and the paper now looks like this. Let's see if we can draw the neighboring lines in this, the same coordinate lines as we had before. So these are the x equals to constant lines, and then these are the y equals to constant lines, and obviously they will look different, and you can imagine now the lines beyond the cut has also got cut, so they will look discontinuous. Let's now try to see what has happened to our point, which is here. The neighboring lines, which are these two lines, and the neighboring points, which let us try to draw, are these. Remember that initially there were 8 points, so now I am trying to draw all of them. But if you can imagine, along this line where I have cut, then 1 point has actually become 2. So there are 1 extra point now. So what is that we see when I compare these two and in this transformation? First of all, each point in the first before transformation are not only 1 point after transformation. Now there can be more than 1 points for 1 point before transformation. The upper part, as I have just shown here, has got become separated, and these lines, these two lines, were actually the same line. You see, the points which were in the neighborhood earlier of this point doesn't stay in the neighborhood anymore. The lines also doesn't stay in the neighborhood, and for one point in the figure of before transformation, there are more than one points after transformations. So that's interesting. So what we say is that these two figures does not have the same connecting properties. The transformation from here to there is such that they doesn't have the same connecting property. The connectedness or the connecting property between the two spaces here are called the topology. So we can also say that these two figures, these two spaces here, doesn't have the same topology. The topology for these two are different. So I call them topologically different spaces. Okay, so what we have seen that we have gone from one space to the other in this case, and we have not preserved the topology. So you see, previously discussed about the metric properties of the space. Now we talk about two different transformations. In one case, the topology is preserved, the connectedness is preserved. In the other case, it is not. In fact, in this case, also the differential property which was there here is not the differential property there. So again and again, let me tell you that they are not topologically equivalent. And we'll see that how these ideas are important and how they play a role in the classical mechanics. Okay, so we learned that we deal with spaces, and the spaces has two different properties that we have learned. One is the metric property, which we discussed here in length, and then we also discussed about the topological properties, how to have same and different topology. And I gave you some examples of how the metric is different even if the coordinate systems are same. If I choose two different spaces, one is the surface of a sphere and the other is 2D Euclidean space. And I gave you a small exercise, if you remember, to write this dr square down instead of dx square and dy square only, which is writing down the writing down the metric on the surface of a sphere in the Cartesian coordinate, 2D Cartesian coordinate system. Okay, so this is what you will practice till the next class, and in the next class we will start classical mechanics.